Okay, so the next topic, so we did frequency and period, so, just sort of getting into the vocabulary. There was two terms to describe oscillatory motion, but eventually we ended up talking about simple harmonic motion, which is sort of a special kind of periodic motion that was basically the topic of quite a chunk of the first exam. And we first started talking, before we started talking about, I guess, purely the kinematic, certainly the energy, we first started talking about the kinematics. So I eventually try to convince you through either the circle, comparing the circular motion to the linear motion of the mass in the spring, that the object in simple harmonic motion moves as a sinusoidal function. And you can decide on what type of trig function it is, whether it's a cos, a sine, a negative cos. All depends on the initial conditions. And our textbook decides to take this convention that the object always starts at positive a at time 0. So if that was a mass in a spring, you would put it out to plus a at time 0 and then let it go. If that's the case, and as I mentioned here in the bold bullet, is that this equation, a positive cosine equation, has to give you the maximum value of the amplitude at time 0. That's what a cosine function does. So cosine function oscillates from starting at 1, eventually going to -1, back to 1. So, but as I mentioned, because our textbook, so this is where I kind of stuttered when I did the lecture. Now that maybe you've seen some of the practice exams, I've sort of had questions where, suppose that the person starts timing the position when it's moving to the equilibrium position to the right, moving to the equilibrium position to the left, maybe when it's at -a. So then but I won't do anything in between. It'll either be a cosine, a negative cosine, a sine, or a negative sine. I won't do anything funky where it's starting at a/2 at time 0. You need phase constants for that. But that's where I kind of stuttered to say I'll always do this, but this is where our textbook is. But you will see questions where I switch it up slightly. But if it does start at a at time 0, this is the x as a function of t equation. Sometimes you'll see the x as with a small parenthesis t to say the position is a function of time. A is a constant, the amplitude, the maximum value. T, the uppercase T, is the period, the time to repeat the function, and yeah, that's about it. What else do I have here? So if you take the derivative of the position as a function of time equation, dx dt, that's by definition v. So you don't need to go through the calculus. You can if you like. But if you do the calculus on that, take the derivative of that previous equation, you'll end up with the velocity equation, a omega. So again, the term in front, so if you take the derivative of a cosine, you end up with a negative sine. That's where you have the negative sine piece here. So the negative is not associated with a omega. It's really associated with the sine function. Then you have another omega in here, and omega itself is 2 pi over t. So in the previous graph, I wrote 2 pi over t. So the omega here, some of you call it the squiggly w, it is a Greek symbol. So the a omega, of course, has to be the v max. So the maximum value of sine omega t is 1. So the maximum value that the v can have is a omega. So it oscillates from having a maximum positive velocity of a omega going to the right through the equilibrium position, or it has a maximum negative velocity of negative a omega when it goes through the equilibrium position to the left, or whatever way you define your negative direction. And then if you take another derivative of the v equation, dv dt, you end up with negative a omega squared negative cosine omega t. So that means that if the x is a cosine function, the a is a negative cos. And then again, the term here is the maximum value a omega squared. And omega is related to, of course, the period, which is basically changing the angular position 2 pi radians over the full time it takes to do that period. And it's also, of course, linked to the k over m for a mass spring system. Do I have any other stuff here? No. So in those two slides, basically these two slides are on the kinematic equations for a simple harmonic oscillator. These will only work for a mass on a spring. do not apply these to a pendulum. A pendulum is not a one-dimensional. It's an object that does not move in a single dimension; it moves in 2 dimensions. So this is x, v, and a are all describing, basically a single linear acceleration. So it is a linear equation, but the speed of a pendulum bob has both an x and y, and you'd have to do the sum of the x and sum of the y. But we don't get into that too much. We don't get into that at all. Hand up here.
So if it's going to the right, it's plus charge plus, and if it's going to the left, is it negative? You said we have to compare cosine minus cosine, sine minus sine. So if it's going opposite on the force, is it plus?
Is what plus?
Is it like plus cosine?
When you refer to the it, what are you referring to? When you say is it, what is the it? Is it the position, the velocity, the acceleration?
I mean the position.
So if you, I'll do this just in a blank slide. So try to fit them all here. So this, oh, you can. Oh. Okay, so this is x versus t. So this is x equals a cosine omega t. When it starts at x equals a, so at t equals 0, x equals a. And it's at rest at that point. It's not moving at all. And then suppose if I had a situation where I told you that the person doesn't start measuring the position of the object until it's moving to the equilibrium position to the right. Well then, so as I start my stopwatch at time 0 when it's moving to the equilibrium position and it's moving to the right. So it would be starting here and then it would go to the right, which is going in the positive x direction. So if that's the case, then this function would be a sine. And if I then said that it's moving through the equilibrium position at time 0, but it's moving to the left, I would then have a negative sign, right? And then the only other, there's everything in between, but as I mentioned, I won't be that cruel. So if it's then, if the person said it doesn't start the stopwatch until it's when it's at negative a at time 0. But it can only, there's only one place it can go from negative a, and that's back in the positive direction. And this is x equals negative a cosine omega t. And that will change every other function. So the v is only a negative sign when the x is a cosine. I'm not sure how much this stuff you would have done in high school, taking derivatives of trig functions. But that's what you, to go from x to v, you take a derivative, to from b to a, you take another derivative. But you can also do it qualitatively and think about, if it begins at a and negative a, it has to be at rest. If it's moving to the equilibrium position, it has to be moving in its maximum speed, not max velocity. You have to figure out what the absolute value of the max velocity is. So at this point, it's moving in its maximum positive velocity. Here, at this point, it's moving in its maximum negative velocity. And this, if it starts at 0, moving to the left. That's also another way to, and I've done practice exam questions like that, I think. Any other questions on kinematics of SHM? No? Okay.